Beneath these roofs, there are more square feet of car production than at any other factory on Earth.
Making a car, it's the great master arts of the 20th century.
The Wolfsburg plant in Germany has over 12 miles of automated assembly lines manned by around 6,000 high-tech robots.
It takes really ingenious engineering to make everything happen smoothly. Every 16 seconds, a finished car leaves the production line.
Even that is not enough. The plant now aims to build 1 million cars per year. From the outside, it's impossible to tell what engineering innovations could make this incredible target a reality. For decades, the red brick production halls of Germany's Wolfsburg car plant have set a benchmark for factory design.
The sheer size of this factory is astounding. The area is nearly 3 times the size of Monaco.
These are more than 100 workshops on this site. It is like a self-contained town.
Inside this factory, there is everything needed to turn raw materials into finished cars at extraordinary speed.
It would not be possible without highly efficient, highly state-of-the-art machinery. This is a result of 80 years of relentless development and advancement in technology.
The plant's current success negates a dark past. It was founded just before the Second World War, specifically to make the cheapest cars possible.
Right behind me, this is the original part of the factory as it all began in 1938.
The Nazi Party had swept into power. One of Adolf Hitler's ambitions is to give his followers mobility by creating a people's car, or Volkswagen. So he enlists car designer and future Nazi Ferdinand Porsche.
Ferdinand Porsche worked very closely with Adolf Hitler in the creation of the original Volkswagen. Hitler set for Porsche very serious demands, and most challenging of all was his requirement of a selling price of only 1,000 marks. Now, 1,000 marks in those days might have bought you a used motorbike.
At the time, German factories like Opel's Rüsselsheim plant couldn't build cars cheaply enough. There was only one solution, a brand new plant built for a revolutionary type of manufacturing.
If you want to make a large number of cars quickly and cheaply, then mass production is really the only game in town.
Real mass production was not known in Germany. Porsche realized that if he were going to meet these goals, he would need to know more about how American cars were manufactured.
Porsche heads to America to meet Henry Ford, the mass production expert. His Rouge River plant is legendary for speed and efficiency. And crucially, it has its own rail network.
Porsche took away from America the most advanced production facilities and concepts that existed at the time. And they incorporated them in the design of the new factory.
But the Nazis had a problem. Where to build their new factory? It had to be centrally located and have good transport links. They settled on Lower Saxony, an area well served by railways and close to an iron mine.
Well, the site was situated here because it was in the middle of Germany in 1938, and everything that was needed to manufacture cars was available out of a surrounding distance of around 30 miles.
Construction begins on one of the Third Reich's most ambitious projects. Taking their cue from Ford's factories, they build an imposing function-driven complex with regular bastion-like external stairwells, skylights throughout, and even a dedicated power station.
The production volumes that they aimed to reach, up to 800,000 cars a year, were far in excess of anything in Europe, and in fact exceeded most of the car production by companies in America.
The Nazis pour over $500 million in today's money into the factory and start building an entirely planned new town for thousands of workers. In just over a year, the first 4 halls are ready to start making Hitler's Volkswagen, the car that would go on to become known as the Beetle.
They invested in the very, very best equipment. They had an extremely advanced press shop. They had one big press that could stamp out the whole roof of the Beetle.
But Hitler then starts the Second World War, and the Wolfsburg factory is repurposed to make military vehicles and munitions. The Nazis staff it with forced workers. Many come from concentration camps, and they are brutally treated by the factory's SS guards. In 1944, the factory is almost destroyed.
During the war, the factory was bombed, and a fully loaded Lancaster bomber had piled into the biggest hall and gone through the roof and caused tremendous damage.
Instead of that being the end of the factory, it's rescued after the war by the British. In 1945, Major Ivan Hurst oversees repairs and arranges the order of 20,000 of the strange cars the plant had been designed to make. The Beetle press equipment had been spared, so the factory quickly starts production.
It hadn't 4 doors. It had the engine in the wrong place. It had not enough trunk space. It had not enough heating. But fortunately, the customers from all over the world decided differently. We started producing first in December 1945, and 10 years later, we produced the first million Beetles, which was an unheard number in Europe.
Despite its failings and its association with a Nazi dictator, the Beetle becomes a worldwide sensation. By 1972, it is the biggest-selling car of all time. And as its popularity grew, so too did the Wolfsburg factory. Today, it has more than tripled in size. It spreads across 70 million square feet, the largest area of any single car plant in the world. The brick production halls still form the heart of the operation. But the Beetle presses have been replaced with 4 gigantic press shops, making almost 500,000 body parts per day. And the assembly lines are now staffed by about 6,000 high-tech robots. Every day, they're capable of assembling up to 3,500 cars. The original power plant has been expanded, and linking this vast site together is an extensive private rail network.
This is Europe's largest private train station, and there's more than 40 miles of rail tracks on the factory premises.
Every day, more than 1,600 tons of steel is brought into the plant.
Altogether, we have 11 wagons per day coming in with raw material.
It is an incredibly challenging task to deliver all the freight into this factory.
Directing each train to the right part of the plant would be impossible without a sophisticated control system, managed from this tower.
We have 3 colors of lines. On the yellow line, we have 3 tracks. On the red lines, we already have some rail wagons standing. And on the blue lines, like here, are actually trains driving.
The operator has control of 150 shunting switches, which allow trains to change lines and head directly for their allotted destination building.
for efficiency, the trains are transporting the materials right inside the workshops.
This train is delivering 24-ton rolls of raw steel. Once inside the depot, specially made cranes unload the rolls directly from the train carriage and place them on giant cutters.
So the first step in manufacturing is turning that raw material into components. We would take the uncut steel and form the shapes of the door, of the hood, the trunk, the wing. So the first challenge is to keep up with the pace of production and assembly. You need machines that are fast enough. The equipment used to build the original Beetle could never cut it.
The original Beetle presses were enormous machines that stamped the body panels into shape.
It used to be pretty exciting to see operators putting sheets into these presses and then standing there as this immense press comes down.
But these presses had a major drawback. They had to be loaded by hand.
We're just losing time at every step, while those human operators try to meticulously line up that steel to make the perfect final component.
Today, the factory must produce 10 times the number of cars it used to when it was making the Beetle.
Manual feeding could not be plausible today in a press shop.
There's no way that hand-fed presses can make parts fast enough. Germany's Wolfsburg car plant is more than 16 million square feet larger than its nearest rival, South Korea's Ulsan Auto Factory. And demand for body parts is relentless. Housed in the rear hall of the original Wolfsburg factory, enormous pressing machines need to spit out more than 5 body panels per second.
The press shop at the factory is serving not just this factory, but the group across the world. Almost 500,000 body parts get manufactured there a day.
This phenomenal output is thanks to a revolutionary panel pressing system. 6 of the heavyweight industrial beasts are linked together. Mechanical arms with suckers maneuver the steel from press to press, with more precision and speed than people ever could.
They're linked together almost as in one machine, and then the steel can move through each press automatically to form the correct shape and part.
These presses are enormous, and in order to exert enough pressure to bend the steel, they need to press down with a force of about 8,000 tons. The only way to generate a force that big is to use hydraulic pistons to squeeze those presses together.
Each press slams the steel plate further into shape, and the line delivers a constant flow of identical panels. But unfortunately, linking the presses only solves one problem.
Obviously, the factory needs to make all the different components for a car, from the bonnet to the doors to the roof. And you can't have a separate press street for every single component. It's just not feasible.
Each press shop must be versatile enough to make different components.
Inside each press is a die. They're actually what forms the shape, the cookie cutter of the component.
To make different parts, new dies must be swapped into the presses. But it's a massive operation.
Traditionally in the industry, it took about 2 to 3 hours to change the dies because it's quite a difficult job. The machine is sitting idle during that whole period. It's not doing productive work.
Leaving presses inactive for long would slash production. Engineers had to come up with a solution.
New processes have been developed to reduce this changing period from a matter of hours to a matter of minutes. There are doors on either side of the press street. The replacement die is craned in onto rails. The door opens and the old die goes out and the replacement die simply rolls in. It is no longer something that stops or slows the production process.
The presses can now run almost 24/7, but this puts tremendous strain on the machines.
The dies are not necessarily delicate. However, it is machinery, moving and grinding almost non-stop. So equipment can wear, problems can arise.
A single press malfunctioning could be catastrophic.
If the presses would break down, we wouldn't have the body parts to make the body shell, and everything would stop.
But maintaining them is easier said than done.
These panel pressing lines are enormous, fast-moving, heavy, noisy machines. And that means it's incredibly difficult to find faults before they arise. They don't want to stop the machine and go in and check it. So there needs to be a way to identify those faults before they become serious in this incredibly challenging environment.
One innovative way that faults can be identified is by listening to the machines.
Nope, perfect. This is the acoustic camera from the press shop Wolfsburg. We have one camera and 48 microphones.
The acoustic camera is pointed at one of the press shops, where it can listen to a machine as it runs.
What just sounds like a huge machine clanking to you and me actually has a unique and precise acoustic fingerprint, which this camera can listen out for.
It's like the doctor who checked the heartbeats from the patients.
The camera produces a waveform, a visual representation of the sound the machine is making.
Any deviation from that acoustic fingerprint recorded while the machine was working normally allows them to narrow down exactly what might be going wrong and diagnose problems before they become serious.
Mit der Kamera kann ich Anormalitäten sichtbar machen. Das heißt, wenn ein Lager ein nicht normales Laufgeräusch macht, was für den Menschen gar nicht zu hören ist, für die Kamera ist das kein Problem.
Today, the waveforms match. There are no faults. The factory's next challenge is to put all the components together to make cars as fast as possible. Body panels and other parts travel about 3,000 feet to the halls near the power station, where a daily engineering ballet takes place on the assembly lines.
So Wolfsburg's goal is to increase production to nearly 1 million cars a year. So to get anywhere near that number, it means employing robots, and in their thousands.
Each car comprises around 10,000 components, so putting them together is a Herculean task, even for a forest of high-tech robots.
This can be like watching a great performance. The sounds moving in sync and harmony, and the dancing across the rhythms. It's almost like a hypnotic state, although it's super highly programmed and planned right down to the last detail.
Each individual part must be fixed not just in the right place, but also in the right order. And this largely automated assembly line is one of the fastest there is, the result of an extraordinary evolution.
Assembly lines are absolutely central to the concept of mass production. They allow creating a product to be split up into a series of discrete steps, and then they can work one after the other, continuously assembling products as rapidly, efficiently, and cheaply as possible.
The first assembly lines revolutionized car production with a simple idea. Instead of making workers move from one stationary car to another, the car moves on a conveyor to stationary groups of workers.
This did create a big increase in efficiency, but really it was nothing compared to what we would later see with the introduction of robots and automation.
But programming robots to be faster than people is a difficult, highly complex task.
So the human has hundreds of thousands of years of trained experiences, visually, sensory, and motor skills. And to put this into a robot is very challenging.
Germany's gigantic Wolfsburg car factory relies on assembly lines staffed by around 6,000 robots. The first was introduced here in 1973. It could only perform simple welds. Just a few years later, robots are omnipresent on assembly lines. But the brute force some are capable of is a serious hazard.
They are potentially dangerous and can cause injuries to humans that are moving in the same workspace. You can see that 200 to 400 pounds of payload can actually harm seriously the human.
There have been fatalities. On January 25, 1979, Robert Williams, an engineer at Ford's plant in Flat Rock, was struck on the head and became the first person in the world to be killed by a robot.
So the robot that would have killed Robert Williams at the Ford factory back in the 70s would have been a pretty simple robot by today's standards. So one of the things that really changed the intelligence of the robot itself is the microchip.
At a cost of at least $100,000 each, these super smart robots are some of the most dexterous. Inside each of their joints is a step motor. This rotates in small increments, and the arm can hold its position without the needs for brakes or a clutch. The software that runs the robot's onboard computers took more than a year to write, but it enables them to move in 6 axes, only one less than a human arm. They can spot weld, clip, or apply glue with exceptional accuracy.
They're very good at repetitive tasks. They don't get tired or bored like humans would.
Robots execute these tasks 24/7 over an entire week, as often as needed, at a very high quality, at a very high accuracy.
These are, in many cases, very large pieces of machinery, and there have been some examples, unfortunately, of tragedies even in recent years. In 2015, in Kassel, in a factory in Baunatal, there was a worker who was crushed under a metal plate, for example. These accidents, they are accidents, they still happen, and robots need to be treated with respect.
Around 65% of Wolfsburg's vast floor space is dedicated to these assembly lines, where the aim is always to get the robots to work faster. But the relentless high output can become the victim of its own success. It creates a fundamental dilemma: how to keep the robots supplied with components.
It's an enormous challenge to coordinate that all components and all parts are just in time at the right place of work at each assembly line.
Traditionally, parts were stored next to the assembly line.
If you do that, what you end up with is a warehouse full of parts waiting to be put into cars. And that's what the Japanese call muda, or waste. The first time the Japanese went to Porsche to look at their operations, they looked around and they said, "Where is the factory? This is the warehouse." Because along the assembly line there were big boxes of parts waiting to be put into cars.
At Toyota's Karamo factory in Japan, Kichiro Toyota was the first to develop a radical new system that does away with the need to store any parts at all. It's known as just-in-time delivery.
The concept today is to make the part, install it, and do it quickly and not waiting around.
It means that each robot receives parts just when it needs to install them, and not before.
The fact that you don't need to store loads and loads of components just in case means that you can save a lot of money and space on warehouses.
It's hyper-efficient, but it's also high risk.
You need to make sure that every single stage of the process is perfectly optimized, as the name suggests, just in time, because any slight delay can radically delay the whole of the production line.
It only takes one bolt to be delivered late, and the entire system will grind to an expensive halt. Orchestrating it is a colossal task that takes place at the factory's control room.
We're standing here in the middle of the brain of the Wolfsburg factory.
Computers break the assembly line down into distinct beats that are completed at different stations, roughly 20 feet apart. After the chassis is completed, the doors, roof, and hood are attached.
So the assembly line has an average beat of 60 seconds. And this means that in every beat, another part is installed. The parts have to be in position at exactly the right moment to make sure they're installed in time. We achieve this by delivering the parts in an exact sequence.
The drivers follow a strict timetable. But there are over 10 miles of potential delivery points in the factory.
The robot waits for no man, or machine for that matter.
The factory roof is fitted with a monorail system capable of delivering 100 parts per hour. Any mistakes will cause problems for robots further down the line. But that's nothing compared with the danger inside the sealed paint shop. Inside Germany's colossal Wolfsburg factory, cars travel more than a mile along assembly lines before the body shells are complete and they reach a stage known as body in white. The cars then head north, past the power station, to a hall that's too dangerous for workers to enter.
In a modern factory like Wolfsburg, there are indeed several stages of production in which there are almost no people at all.
Painting releases noxious fumes, but robots are immune.
Painting the body of a car involves usually introducing the particular car into a closed room.
At this paint shop, specialized automatons first dunk the cars into an electrostatically charged undercoat bath.
There are no health issues because we don't have any humans inside this workspace, so the human is actually protected from all these fumes.
Automated gas burners then warm panels to aid the adhesion of top coats.
With Wolfsburg striving to increase production to 1 million cars per year, it does mean that every production stage needs to be highly optimized and use as much efficiency and automation as possible. However, that doesn't actually mean that every stage and process is currently automated, nor will it necessarily be automated.
In addition to all the robotics, the plant has a workforce of more than 60,000 people. The most complex process is building the powertrain. It takes a battalion of highly skilled workers to turn the engine, clutch, gearbox, and drive shaft into a single unit.
The powertrain in a modern car is incredibly complicated because it's made of loads of different components, everything responsible for getting that power from your fuel and converting it into motion.
It has its own dedicated assembly line, which must be perfectly coordinated with the car body it will eventually be installed in. This is a high-risk process, the ultimate just-in-time delivery.
There's no room for error. Every car has its own unique powertrain, and it has to meet the line at exactly the right point for the assembly process.
To make it even more of a challenge, the body and the powertrain are made on different floors.
So the powertrain is made right below this level. There's another level of the production where the engine, the gearbox, the exhaust, the axles, brake lines, where everything is put together to one unit.
Timing is everything. Each of these skilled technicians has to know exactly how long they can spend on each task.
Before the chassis and the powertrain come together, the chassis is basically just a rather elaborate lump of metal. When those two things do finally join is known as the wedding.
At the exact prescribed time, robotic arms lift the powertrain through a hole in the floor.
And this powertrain unit is then arriving here just in sequence. That means at the moment the body shell, which is supposed to get that powertrain, arrives, and then the powertrain is lifted up by an elevator from the ground floor to be fitted perfectly into the body shell.
The wedding sounds incredibly romantic, and it's the first time that this thing becomes a car.
The powertrain is like the groom, and in this case, just happened to be a white bride.
Achieving a successful wedding would alone be a marvel of engineering and logistics if Wolfsburg only made one model of car. But they don't.
The consumer wants to not have the same car as the neighbor, for instance, but they want to drive a very individualized car. So they cannot just produce one car model across the entire line, but there has to be a certain variability.
This factory is making so many different models and specifications of car that it's incredibly difficult to make sure that the right chassis and the right powertrain always meet.
One of the reasons for this factory's exceptionally high output is that different models of car can be built on the same assembly line. But how do the robots know which powertrain, for instance, to install onto which body shell?
The robots on the line are actually capable of making multiple different types of cars. And in Wolfsburg, we see 6, 7 different models, and several of those models come down the exact same assembly line. And the way these robots are so adaptable and can be programmed in so many different functions is really quite amazing.
Every chassis might look similar, but as each one enters the assembly line, a scanner reads a tiny tag attached to its rear, called a radio frequency identification tag, or RFID. This is the secret. The tag holds all the information needed to build the car. The model, the specific set of components, even the color.
They are very similar in a way to the barcodes that everyone knows from the supermarkets. However, these chips are more intelligent.
So the body tracking system, our RFID system, is telling in each and every station what model, what car, what style. As you can imagine, the sunroof is different than a full roof. A right steering wheel car is different than a left steering wheel car.
The data the RFID stores enables the robots to be programmed to make quite different models right next to each other.
So in total, there are 4 production lines in Wolfsburg. We are assembling not just the Volkswagen Tiguan and the Volkswagen Touran. We are assembling here also a car which is not labeled on a VW sign, the Seat Tarraco.
There are so many variations that the probability of 2 identical cars being made next to each other is minute.
Theoretically, it happens once a year that 2 twin cars are leaving the production of this facility.
Crucially, this adaptability future-proofs the plant, because it means that as soon as a new model is approved, it can go straight into production.
We're not just building cars at this facility, we have to keep ahead of the game. That means we always have to design and create new cars for our customers.
Every year, this mega car plant produces enough cars to create a traffic jam from New York to Los Angeles. One of the biggest challenges for mass-producing cars is maintaining demand.
The car market is incredibly competitive, and things are changing all the time.
And to design new cars and the best cars, we need to have the best facilities. We also do research and development processes here in the headquarters of Volkswagen.
They have a state-of-the-art research and development center right here at the Wolfsburg plant.
When you're designing a car, there are lots of different constraints. Some of them are just the laws of physics, but others are making sure that whatever it is you've designed is actually able to be manufactured. And that's why it's really important that the guys in R&D are talking with the people who are actually going to have to build the thing.
Having the designers and engineers in close proximity makes the evolution from concept car to mass production much faster.
Before a car goes into mass production, design does have to meet engineering. And at that point, the engineers get involved and will say, right, actually for this design to become reality, we're going to need to do ABC. There is a massive importance given to testing of prototypes. Precision down to every detail really matters. Having no gaps in the door and no sounds or no sound flushes at any point. Opening and closing doors, testing the suspension up and down in an actual environment. And that is really critical in today's environment.
Inside one of the most recent buildings at the plant is a $110 million test center that can analyze new designs 5 times faster than its predecessor. With high volumes of new models being made, any improvement can be very valuable, and any mistake can be disastrous.
Computer simulations are one thing, but the acid test is to put it in a wind tunnel.
In our original tunnel, we needed up to 30 minutes to load a car. And now we can manage it in under 5 minutes.
It's directly in the middle.
The wind tunnel at Wolfsburg is an absolute feat of engineering. It looks like something out of the future.
This tunnel is very fast. We can simulate driving at 155 miles per hour.
Generating this kind of wind speed requires a colossal state-of-the-art 3,000 kilowatt fan.
This is our fan with a diameter of 26 feet. This is the heart of our testing track.
The pressure to maximize performance is so high that the company broke the rules. Volkswagen's reputation was seriously damaged in 2015 after the company admitted installing software in millions of their cars to cheat emissions tests.
Volkswagen knew of these problems, and when regulators expressed concern, Volkswagen obfuscated, they denied, and they ultimately lied.
The scandal put top executives in jail, and VW had to pay more than $30 million in compensation. Despite this, in 2016, VW became the world's most successful car manufacturer by sales. But building huge numbers of cars creates yet another problem.
It's really critical to remember that the work does not end at the end of the line. We don't build cars just in case we sell them. You'd overrun the factory. There's only so much space available, and how much of that space do you really want to give to turn into a parking lot? You need a really efficient distribution system to move the car from the factory to the customer around the world.
A car can roll off the assembly line and be delivered to somewhere as far away as Shanghai at a phenomenal speed. Wolfsburg builds so many cars that simply shifting them off the site is an industry in itself.
The solution is pretty neat, if not challenging. The same network that brings in the raw materials brings the finished vehicles out, and that's principally the trains.
Every working day, about 1,800 cars leave the factory by freight train.
The challenge is to keep each train's waiting time to the minimum.
Conventionally, you'd use a process known as shunting, which is where you bring in an individual train carriage, load it up with cars, then drag it out again and couple it onto the rest of the train. And you can't do more than one of these carriages at a time. So it's incredibly long-winded and inefficient.
Instead, the Wolfsburg factory has a specially designed multiple loading bay.
We have a big advantage here, working with a sliding stage. It means that we can do 3 work processes at once.
First, cars are driven onto an empty carriage. Then the giant sliding stage moves the full carriage directly to the track, where the engine is waiting. At the same time, cars are driven onto the next empty carriage.
The upshot of this basically is that they can load multiple carriages in much quicker succession.
It enables super long trains to be assembled much faster than with traditional shunting. Every day, around 180 loaded carriages leave the factory. But not all customers want their cars delivered.
The Volkswagen decided, okay, let's invite the people to come here. And they opened the site for the customers and for the visitors.
Some can even collect their new car as soon as it comes off the assembly line.
The customer can be the very first person to sit behind the wheel and drive the car, which for some people is a real thrill.
A few cars travel along a tunnel without their odometers clocking up a single mile to one of the world's most high-tech car showrooms.
The advantage of these towers is that you can store loads of cars, but with a very small footprint on the ground.
But there's no drive ramp. So how do the cars get to their parking spaces? Inside each tower is an automated elevator. Powered by a pivoting 120 kilowatt motor with a 7.2-ton counterbalance, the mobile platform can lift cars and park them anywhere in the tower. It's the fastest automated high-rise parking system in the world.
Vertical system, it works very fast. It needs about 40 seconds, I think, to bring a car up or bring a car down and overhand it to the customer.
In manufacturing, no company can sit on its achievements. Volkswagen recently announced that it intends to invest $50 billion on new factory technology, with a significant amount going to Wolfsburg. As well as electric cars and new materials, they're also developing fully autonomous warehouse trucks.
They are able to make decisions effectively for themselves. They'll pick up material where it's required. They'll go to different stations as required. These are smarter, more efficient robots than we've seen before.
Whether this superstructure will go on to produce 1 million cars per year, only time will tell.
The agenda for Wolfsburg was to really build a car for everybody as cheaply as possible. So you could say that it began life wanting to make cars for the people, and now it wants to make cars for the world.
The plant may have had a dark history, and more recently been embroiled in scandal. But with its commitment to smart technology, it's still as ambitious as ever.